AI data centers have hit a performance wall, but the bottleneck is not the processors, it's the network. In a modern AI factory, the fabric functions as a core part of the compute system, dictating the productive output of the entire cluster. When you run data parallel training, you aren't running independent tasks. Hundreds of accelerators alternate between computation and collective communication, constantly syncing up. This chart shows how synchronization barriers play out. If one GPU lags, the entire barrier holds. Every other accelerator sits idle, waiting for that tail latency to clear. That's why average link utilization is useless here. The only metrics reflecting profitability are job completion time and tail iteration time. To stop massive data transfers, elephant flows, from colliding and causing these traffic jams, your network needs workload-aware path placement and dynamic load balancing. If your network controller is only trying to optimize link occupancy without tying it to the actual workload outcome, it's solving the wrong problem and bleeding your compute budget in the process. This brings us to a massive fork in the road for CTOs. You can standardize on a single vendor's deeply integrated hardware stack, or build a horizontal vendor-neutral control layer across the entire floor. The first route is native integration. Vendors like NVIDIA, Cisco, and Arista are shipping silicon today that actively optimizes these flows at line rate using deep hardware hooks. Let's map this out. We have the neutral overlay approach, PTCP. The incumbents sit here, offering proven optimization, but locking you into their ecosystems. PTCP spans this other quadrant, promising cross-vendor flexibility, but critically, it's a proposed architecture, lacking public evidence it matches native hardware speed. You're looking at a strict trade-off. You have to weigh the theoretical flexibility of seeing across all your storage and compute domains against the proven, hard-coded reflexes of native hardware. Let's look at what that native baseline actually gives you. If you turn on Arista's cluster load balancing or NVIDIA's DOCA, you are tapping into deeply integrated software. These systems handle adaptive routing and congestion management directly at the silicon level. They detect collisions and reroute traffic in microseconds. Because they have those deep hardware hooks, they already solve the most basic, punishing issues of AI fabric congestion. The catch is their field of vision. A fully native setup gets you ultimate performance within its own borders, but leaves you blind to third-party storage stalls, multi-vendor accelerator states, or dependencies running on different orchestrators. The incumbents have already conquered basic adaptive routing. For a third-party control plane to justify its existence, it can't just offer another telemetry dashboard. It has to prove that coordinating across all these different domains actually produces a faster compute cycle. How does PTCP attempt to do that? It operates as a governed slow-path controller. Instead of making split-second silicon decisions, it takes seconds or minutes to evaluate the entire state of your data center before pushing instructions down to the fast-path switches. In PTCP's architectural model, the controller observes telemetry across network, compute, and storage to build a connection model. It evaluates policies, translating insights into bounded actions for existing switches. Finally, it enforces rules in fast-path environments, verifying the outcome to close the loop. On paper, it's an elegant solution. In reality, maintaining consistent state across multiple vendor APIs and constantly translating scheduler insights introduces immense architectural complexity. When you pull all that logic into a central abstracted core, you introduce new points of failure and latency. If the slow path makes a stale decision, it could easily bottleneck your hyperfast hardware. Deploying PTCP means making a calculated bet. You're betting that its broad, cross-vendor perspective can outsmart the localized, ultra-fast reflexes of native switch hardware. There are two specific areas where that broad perspective might actually win out. The first is mixture of experts, or MOE, workloads. These generate complex, shifting, many-to-many traffic patterns depending on which expert is activated. Basic link metrics fail completely here. You could have a perfectly balanced network link that is still feeded overloaded endpoint, destroying your time to first token. The network alone can't fix a bad expert assignment. It requires active coordination with the scheduler, which is exactly the type of cross-domain problem PTCP is designed to solve. The second area is security, specifically mapping out post-quantum cryptography migrations across diverse hardware. PTCP doesn't execute the cryptography itself. Instead, it can create a structural inventory, tracking exactly which paths, modules, and policies across your vendors have been updated to post-quantum standards. This cross-domain visibility is useful for advanced workloads and security audits. But again, the execution relies entirely on the reliability of PTCP's multi-vendor adapters. The market has moved past the days of simple connectivity. Every serious AI network now uses some form of control-rich infrastructure. The question is where your intelligence lives. If you operate a homogeneous AI factory, say entirely built on NVIDIA or entirely on Arista, your path is straightforward. In a single vendor setup, a third-party overlay is likely unnecessary overhead. Stick to the native stack. It is safer, tightly integrated, and heavily optimized for that exact silicon. But if you manage a heterogeneous environment, mixing Cisco networking, third-party storage, and varying compute accelerators, the calculation changes. For highly mixed estates, native controls struggle to cross administrative boundaries. Here, PTCP's vendor-neutral coordination holds massive theoretical value, making it a serious candidate for investigation. If you fall into that heterogeneous category, do not deploy a multi-million-dollar control plane based purely on architectural theory. You need to force a strict empirical proof-of-value test. First, benchmark the native baseline. Measure your optimal job completion time using only the hardware vendor's existing tools. Next, test PTCT on identical hardware, relying entirely on the overlay's logic instead of the native reflexes. Finally, benchmark PTCP integrated directly with those native controls, measuring any synergy and carefully tracking the operational overhead. Your decision gate is simple. Only adopt the overlay if it delivers statistically meaningful improvements to your application-level metrics and perfectly guarantees safe rollback when failures happen. In the AI era, theoretical visibility is nice, but productive compute time is the only metric that pays the bills.